Hello everyone. In the last class we started with the reactions of alcohols and we saw that what are the different ways in which alcohols can react. The reactions could either be due to the hydroxyl functionality involving the replacement of the hydroxyl group, or those in which the hydrogen of the hydroxyl was getting replaced, which were due to the acidity of the alcohols. Then we were discussing further about the reactions where both the alkyl as well as the hydroxyl group both are involved in the reactions, and the first in this series which we took was the oxidation reaction, the oxidation of alcohols to aldehydes, ketones and acids. So, these are the oxidizable functionalities, and the oxidation can be carried out with very many reagents such as potassium permanganate, chromic acid, and these essentially were yielding us the corresponding acid. So, this is what we saw last time, that if you start with a primary alcohol and you carry out its oxidation with aqueous alkaline KMnO4 or with chromic acid, you were ending up with an acid. However, if you want to stop in between, so the first step is that your alcohol is getting converted to the aldehyde and the aldehyde subsequently undergoes oxidation to the acid. So, if I want to stop at the aldehydic stage, what are my options? So, one option is that I either distill off the aldehyde once it is generated, or I make use of milder oxidizing agents which do not promote the further reaction which involves the conversion of the aldehyde to acid. And one such reagent in this category which we started talking about was pyridinium chlorochromate. So, today I am going to start with pyridinium chlorochromate as a mild oxidizing agent for the oxidation of alcohols. So, the general formula for pyridinium chlorochromate, the structural formula is given like this. So, you have a pyridinium cation and a chlorochromate anion. Okay. So, the first thing is that how is this prepared? So, for this you take chromium trioxide and you dissolve it in HCl, okay, and this is followed by treatment with pyridine. So, subsequently you treat it with pyridine and eventually you get your compound which is the pyridinium chlorochromate. This pyridinium chlorochromate is taken in dichloromethane as the solvent and used for the oxidation of alcohols. So, mind you, we are dealing still with the oxidation of alcohols, and in this series I am discussing the milder oxidizing agent like a pyridinium chlorochromate which can be used to stop the reaction at the aldehyde stage. So, now if you start with a 1 degree alcohol and you treat it with pyridinium chlorochromate in dichloromethane, you get the corresponding aldehyde. So, you started with ethanol, you will end with acetaldehyde. So, the reaction stops at this place. Now, you compare this with the oxidation with other chromium reagent. So, you compare it with your other chromium reagents which we discussed last time. If you do the same thing with the Jones reagent, we were ending up with the corresponding acid. The reaction would not stop at the aldehyde stage. Now, if you recollect what is so special about pyridinium chlorochromate which is preventing the further oxidation. So, as you can see here that the conditions which we are using are non-aqueous, okay, and the reason why the aldehyde was changing into acid with the other chromium reagents was that in these cases there was a dihydrate which was being formed from the aldehyde. There was a dihydrate generated from the aldehyde under aqueous conditions. Okay. So, in the presence of water, this is what was happening and this is what was leading to the further reaction. So, since this is taking place under non-aqueous conditions, we are able to regulate the reaction and stop it at the aldehyde stage. Okay. So, this is one important reason why pyridinium chlorochromate is used in specific conditions. Okay. So, after oxidation, now the next reaction involving both the alkyl and the hydroxy group is the dehydrogenation of alcohols. So, we are talking about the dehydrogenation reaction of alcohols which involves removal of a hydrogen. As the name says, you are removing a hydrogen molecule from the alcohol. So, what are the conditions? Which means that if you start with a primary alcohol and you remove a hydrogen, you will end up with the corresponding aldehyde. And how are we able to do this reaction? So, the conditions are quite harsh. They take place in the presence of a copper metal at a very high temperature, 300 degrees centigrade, and this is what leads to dehydrogenation. If you start with the corresponding secondary alcohol, under the same conditions, you will get the ketone with the release of hydrogen. If you start with a tertiary alcohol for that matter, it does not bear any alpha hydrogen. Okay? There is no alpha hydrogen available with the tertiary alcohol, and therefore, there is no possibility of a dehydrogenation to take place, and in fact, this yields you the corresponding dehydration product. So, you get a dehydration with the loss of water molecule from the 3-degree alcohol. All right. Moving ahead, another type of reaction involving both the alkyl and the hydroxyl part is what we just saw with the 3-degree alcohols, is the dehydration reaction. So, dehydration of alcohols, which involves, as the name says, loss of a water molecule. So, what are the different ways in which the dehydration can be affected? We can either have chemical treatment of the alcohol. So, we have chemical methods, or we can have catalytic dehydration of alcohols. So, in the chemical methods for dehydration, you start with the alcohol and you carry out the dehydration in the presence of concentrated H2SO4 or concentrated phosphoric acid. So, these are the dehydrating, and you heat it. So, you are carrying out this reaction, which is nothing else but it is a type of an elimination reaction. So, it is an elimination reaction of an alcohol, and this can involve a rearrangement if it goes via E1 pathway. I am sure you have talked about the substitutions and the elimination reactions. So, under that you would have learned that E1 reaction, just like in SN1, involves the formation of a carbocation intermediate, and this is this carbocation which can undergo rearrangement to give you rearranged olefins. The reactivity for the dehydration would follow the order 3 degree, 2 degree and 1 degree alcohols. This is the order of reactivity. Okay. If you start with a tertiary alcohol, with the tertiary alcohol you treat with sulfuric acid and heat it. In this case, you will get this as your only product. Okay. So, this is the difference in the reactivity, 3 degree being the most reactive as compared to 2 degree and 1 degree. The other method of dehydration we said is catalytic. So, for carrying out the catalytic dehydration, the conditions involve, essentially we use alumina at 350 degree. So, you pass the vapors of alcohol, okay, you pass vapors of alcohol over alumina to bring about the dehydration reaction. All right. So, this is about it, and we now take up another important reaction of alcohols, which is popularly known as haloform reaction. Haloform reaction, it is a popular reaction of alcohols, and the important thing about this reaction is that it is given by those alcohols which bear a methyl group. So, you have to have a acyl functionality. So, if you have this functionality, these are the ones which are going to respond to the haloform reaction. So, what do we mean by that? That means this reaction is going to be shown by methyl ketones. Okay. So, these primarily are the substrates which are going to respond to a haloform reaction. So, you have methyl ketone as a substrate. You can have a secondary alcohol. The condition is that this secondary alcohol should have one methyl group attached to this carbon bearing the hydroxyl, because eventually during the reaction it is going to generate this methyl keto functionality, which is a requisite for it to respond positively to haloform reaction. You can also have primary alcohols, which again during the reaction are able to furnish acetaldehyde or ethanol, which again has the CH3CO unit. So, it is given by methyl ketones, it is given by secondary alcohols, one of the carbons is bearing the methyl, it is given by primary alcohols, the carbon is next to the carbon which is bearing hydroxy, the next carbon is a methyl carbon, and it can also be given by acetaldehyde, and this is the only aldehyde which will give a positive haloform reaction. Okay, so what is this reaction and why are we so specific for these substrate? So, in the haloform reaction, you take the compound, you treat it with the halogen. This halogen could be chlorine, bromine or iodine. This is done in the presence of an alkali, and what you get is the corresponding haloform. When you use chlorine, product is chloroform. When you take bromine, you get the corresponding bromoform. If you take iodine, you get the corresponding iodoform. Chloroform and bromoform are colorless liquids, while iodoform is a pale yellow solid. Okay, this is a pale yellow solid, and that is why this reaction is popularly known by the name iodoform reaction. So, for all the different halogens, it is the iodine which is the most important for this type of substrates, because you get a solid compound which is iodoform, which is yellow in color. Easily you can see that and you can conclude that this particular molecule contains the CH3CO functionality. Alright, so what happens in this reaction? With the alcohol, this reaction requires 3 steps. If you start with the alcohol as the substrate, the first step is the oxidation, the second is the halogenation, and the third is the hydrolysis. So, if you start with an alcohol in which the carbon bearing the hydroxyl has a methyl attached to it, then it will involve an oxidation followed by halogenation followed by hydrolysis. But if you directly start with an aldehyde, which is acetaldehyde, or a ketone bearing which is a methyl ketone, in this case it will only involve 2 steps. Okay, with these ketones it will only require 2 steps, which are the halogenation and hydrolysis. So, only 2 steps are required with the ketones, because you do not need an initial oxidation. So, if you look at the reaction, the overall reaction, let us see what happens with ethanol. Let us say we start with ethanol as your starting alcohol. Okay, the first step is, it is a 1-degree alcohol with the halogen under alkaline conditions. It produces the corresponding aldehyde along with formation of NaX and water. So, if you balance this, you require 2 moles of NaOH to gives you 2 moles of NaX and 2 moles of water. So, essentially what is happening initially is that your NaOH and your halogen, let us say it is a chlorine, it is providing you the corresponding hypochlorite. So, it is a sodium hypochlorite and NaCl and water. This is essentially what is happening, and this is the oxidizing agent which is actually responsible for oxidizing the alcohol to the aldehyde. This is the first step, which is the oxidation. The second step is halogenation, in which once you get the corresponding acyl functionality in the presence of halogen and base, all the 3 alpha hydrogens of the aldehyde or the acyl unit, all the 3 alpha hydrogens are replaced by the corresponding halogen, and you get this kind of a product along with formation of NaX and water. So, if you balance this, you require 3 molecules of halogen, 3 of NaOH to give you 3 of sodium halide and 3 of water. This is the second step, which is the halogenation, involving complete halogenation of the alpha hydrogens. The third step is the hydrolysis of this trihalogenated compound under alkaline conditions, and this yields you the corresponding product, which is your haloform. So, this is what your haloform is, along with formation of HCOO(Na). So, if I write the overall equation for all the 3 steps, the oxidation, halogenation and hydrolysis, I combine all the 3 steps. So, my overall equation for an alcohol haloform reaction becomes that 1 molecule of alcohol will react with 4 molecules of the halogen and 6 molecules of NaOH to yield the corresponding 1 mole of haloform, sodium formate, 5 moles of sodium iodide and or sodium halide, and 5 moles of water. So, this is the overall balanced equation for a haloform reaction involving an alcohol. The same thing if you carry out with an acyl unit. Okay. If you do the same thing with an acyl unit, so what is the first step? The first step in this case is going to be directly the halogenation using the halogen and NaOH to give you the halogenated ketone along with formation of sodium halide and water. Again, if you balance this, it requires 3 moles of this, 3 moles of this stoichiometry, and this is what we get. The second step is the same, which is the hydrolysis of the halogenated ketone, and you treat it with NaOH, again 1 mole, and you get your haloform along with formation of sodium salt of the corresponding acid. So, overall the equation for the haloform reaction of acyl ketones would involve the following stoichiometry. You start with 1 mole of acyl ketone and treat it with 3 moles of halogen and 4 moles of NaOH. So, this is the stoichiometry requirement of the base and the halogen in the haloform reaction. You end up with the haloform and the sodium salt of this acid, 3 moles of NaX and 3 moles of water. So, you can see the difference when you are using, starting with this, the requirement of the halogen and the base is lesser, obviously because of obvious reasons. The first step is not involved here, which is the oxidation. Okay, so, this is the overall equation reaction for the haloform reaction. If we look at the mechanism, the mechanistic steps in little more detail. So, the first step is the oxidation, and the oxidation is by the presence of the halogen and the base, which is forming the sodium hypochlorite, and so this we already done. The first step, you are generating this. Okay, the second step is your halogenation. Now, in the halogenation, you are having a carbon next to a carbonyl, which is electron withdrawing carbonyl, and each of these hydrogens, the alpha hydrogens, is slightly acidic because of the presence of the carbonyl adjacent to it. So, in the presence of the base, what happens is that the base comes and abstracts this proton, so that you get an intermediate which is next to a keto. So, this you know is nothing but an enolate. So, you are generating an enolate which is a stable species here. You can write this as the resonant hybrid structures for this enolate. So, you get this enolate in the second step. Enolate or your carbanionic form of this compound is what picks up the halogen. So, you have your halogen which is slightly polarized and it picks up this halogen, and what you get is the corresponding monohalogenated product. Okay. You get this monohalogenated product, and then this subsequently undergoes halogenation twice with 2 molecules of halogen, and finally it gives you the trihalogenated compound. So, this is happening 3 times successively in the halogenation step, so that finally you get the trihalogenated product which undergoes hydrolysis in the next step. So, you have this trihalogenated ketone which in the presence of the base attacks the carbonyl, okay, and you have 3 electron withdrawing halogens attached to this carbon, and this attack of this hydroxyl. So, eventually this loses the CX3 functionality and you get this molecule, and this abstracts this proton from the acid. So, there is a proton transfer, it abstracts the proton from the acid and gives you the corresponding haloform. So, you get the haloform along with the formation of the corresponding carboxylate anion, which can again take up the proton to give you the acid. So, the importance of this reaction, if you see the application and the importance of this reaction, is that it can distinguish those aldehydes and ketones, which aldehydes is only acetaldehydes. It can distinguish those ketones and alcohols which have a CH3 CO unit or which are capable of generating the CH3 CO unit in case of alcohols. It is also used for the preparation of chloroform, bromoform and iodoform. So, these are used, this is a local anesthetic, this is a general anesthetic, and this is an antiseptic. So, it is used for the preparation of these compounds. So, this is an important reaction. I would also like to comment on the substrates which would give a positive haloform reaction and substrates which would not respond to the haloform reaction despite of having an acyl unit. So, let me show you few examples. If you take acetic acid and you subject it to iodoform reaction, you do not get any yellow PPT, okay? It responds negatively to this reaction. Likewise, if you take another acid derivative, you take acetamide, you take acetyl chloride, acyl chloride, or you take the methyl ester, each of these give a negative iodoform test. So, in general we say that the acid and acid derivatives other than ketones, okay, and aldehyde is your acetaldehyde, they do not give positive iodoform reaction. So, now you rationalize and think, why is this happening? So, you recollect that we are carrying out this reaction under alkaline conditions. So, if you have an acid, this is the most acidic proton of the acid. Okay. So, under alkaline conditions, what is going to happen? This is immediately going to give you the corresponding sodium acetate. It is going to yield you the corresponding anion, which is quite stable, and this is not going to. So, this is already a charged species, the molecule is already charged now. So, now the deprotonation of these alpha hydrogens is going to be very, very difficult. Also, there is going to be a problem in the last step, in the hydrolysis step. So, what is happening in hydrolysis? So, we just saw that during the hydrolysis, the base is attacking the carbonyl, but in this case, even if you are forming the halogenated product, the base is not going to attack on the carbonyl, but rather it is going to pick up this acidic proton and form this. So, you already, because you have a carboxylate ion in the system, right. So, the nucleophile is not going to come and attack on the carbonyl anyhow. So, this is the reason why an acid will not work out positively iodoform reaction, and on the similar rationale you can imagine why an acetamide will also not work under these conditions. Again, this amidic proton is relatively acidic, and it is going to give you again this two resonating structures, and it will be incompetent, not capable of pursuing further the iodoform reaction. In case of an ester, however, the first thing, this is going to hydrolyze under alkaline conditions and yield the corresponding acid, and then the same problem which we witnessed here with the acid is going to become evident here as well, because it is because of the reason why even the esters would not respond to an iodoform reaction. But if you take the compounds which have active methylene groups, okay, active methylene compounds, the diketo compounds, if you take this compound and you carry out the iodoform reaction, this is, so between this alpha hydrogens and these two alpha hydrogens of the active methylene CH2, since the active methylene CH2 is more acidic, so it is going to give this particular halogenated product during the halogenation step, and then this is followed by attack of the alkali, and as expected, okay, you will get this corresponding anion along with formation of acetic acid, and it picks up this proton and it will give this product. So, with active methylene containing carbonyls, this reaction will go. Likewise, if you have, instead of a ketone, you have an aldehyde at these two terminal positions, even this is going to give a positive iodoform test, just the way we have seen with this active methylene compound. Okay. So, this is about alcohols, their reactions, the important reactions we have covered. Haloform reaction, although it is a reaction of the acyl compounds, the ketone, the methyl ketones, but again it is very important for alcohols as they can be oxidized under the haloform reaction conditions to the corresponding methyl ketones. So, now moving ahead, we have talked about the monohydric alcohols. Now, we will talk about the dihydric alcohols or glycols. So, if you recollect, in the first few lectures we talked about the synthesis of these glycols, right. So, if we want an alcohol which has two hydroxy groups, adjacent carbon atoms, that is what we were calling glycols, and we are talking about what are different methods of synthesis starting from alkenes. So, now we will go a little more descriptive on these glycols and the important reactions they undergo in today's class. Okay, so we start with glycols, which are dihydric alcohols, and the general formula is this. So, you have 2 hydroxyls on 2 adjacent carbon atoms, and we can have different types of these glycols. If you have both 1 degree, you call this as ethylene glycol. We talked about even the physical properties of glycols when talking about if it has more than one hydroxy group, what is going to be the impact on the boiling points of these molecules by virtue of the hydrogen bonding. If you have a secondary alcohol here linked to a 1 degree alcohol, this 1, 2, 3 carbon, so we call this is a propylene glycol. Okay. If you have another example, you have a 3 degree alcohol and this is linked to this 1 degree. Okay. So, you have a 2, 3, 4 carbon system, and if you have to start the numbering, it is a 1, 2 diol, and it is a 2 methyl propane 1, 2 diol. Okay, so you have many different examples of glycols which you can have. If you have, suppose, both the carbons as tertiary carbons, okay, which are bearing the hydroxy group, both are tertiary carbons. So, this is an example where both the hydroxy groups are present on the tertiary carbon atoms. These kind of diols are called pinecols. Pinecols are those diols in which both the carbons are tertiary carbon atoms. Okay. So, if you have, this is a phenyl and a diol. So, this pinecol is called Benz pinecol. This is the common name, and if you have to give the IUPAC name, it will become 1, 1, 2, 2 tetra phenyl 1, 2 diol. Let us move on to the synthesis of these molecules, the glycols. So, one of the ways you can have different starting materials. Okay. So, the first one, as we discussed, as I was telling you in the previous classes, was starting from alkenes as substrates, and if you recollect, please check back the notes. We started with alkenes as substrates and we said different methods for synthesizing diols. One was using aqueous or alkaline KMNO4, and if you remember, this was giving us a cis dihydroxylation. Okay, this was a cis dihydroxylation. The same thing was happening with osmium tetroxide, which one or treatment with of alkenes with osmium tetroxide was again giving you a dihydroxylated product. You could also make an epoxide out of an alkene followed by an acid catalyzed hydrolysis, which was also giving you an alkene. And another example method and strategy which we discussed was with the hypohalous acids followed by hydrolysis. If you recollect, I will just write it down in case you do not remember. You had an alkene, you treat with the hypohalous acid, okay. And what was happening? A regular addition reaction on alkene, electrophilic addition, and this was followed by hydrolysis. So, you carry out sodium carbonate hydrolysis and this yielded the corresponding diol. So, these were the different methods which we discussed for carrying out the synthesis of the diols starting from alkenes as substrates. Okay, the next method for the synthesis of diols is starting from alkyl halides. Right. So, from alkyl halides, the conditions which are employed are you carry out the hydrolysis, simple hydrolysis with the carbonate solution, okay, which means that you have to have a dihalide to begin with, right, and you treat it with sodium carbonate, aqueous conditions, you get the corresponding diol along with the formation of sodium chloride and release of carbon dioxide. However, the disadvantage with this reaction is that the yield of the diol which is obtained is poor. So, it is not, frankly speaking, a very good method. So, a revised version of this method would be that you start with the same dihalide, the dihalo compound, and you treat it with fused sodium acetate. Okay. Treat it with sodium acetate. This is an alternate route, and you end up with the corresponding diacetate, which is a glycol acetate, and this under acid catalyzed hydrolysis furnishes the corresponding glycol in high yield. So, this is an improvised version of the hydrolysis of the dihalides for obtaining these 1,2 diols. Okay. The third substrate from which you can get the diols is from alkylene diamine. So, we started with alkenes, then alkyl halide, and now alkylene diamine. So, alkylene diamines, you have to convert this into a diol. Okay. This is what you want from it. So, what is the immediate thing which comes to your mind? What reagent should we use? So, we treat this with nitrous acid. For the amines, treatment with nitrous acid is what is prescribed. You treat it with 2 moles of HNO2, which can be formed from NaNO2 under acidic conditions, and you will get this diol along with release of nitrogen gas and water. So, this is another method for synthesizing the diols starting from alkylene diamine. Another method is, as we did previously also, reduction of the carbonyl compounds give alcohols, simplest of all. So, you carry out in this case also reduction of various carbonyl compounds, and in this case the preferred choice of reduction is that we carry out electrolytic reduction. Electrolytic reduction of the carbonyl compounds. So, if you start from glyoxal, which is the dialdehyde, you carry out electrolytic reduction, you get the diol. The same thing can also be achieved starting from the diester, which is the diethyl oxalic acid ester. So, oxalate, again you can carry out the same thing. This involves loss of 2 molecules of the alcohol. You can also get the same compound starting from half aldehyde, which is glycol aldehyde, to give you this glycol. If you have a keto and aldehydic group, which is a pyruvic aldehyde, this is also susceptible to electrolytic reduction to give you the corresponding 1,2 diol. So, all these different methods for the synthesis of the 1,2 diols involve the starting compound as a carbonyl functionality. So, now we proceed with the reactions of glycols, and as we did previously for monohydric alcohols, the reactions can be broken up in two categories. One, due to the hydroxyl group, okay, and others which involve both the alkyl and the OH group. In the hydroxyl group, you can further differentiate those which involve the hydrogen atom loss and those which involve the entire OH group replacement. So, as we did previously for the alcohols, the reactions involving the hydroxyl group, you have the action with sodium metal, which involves the acidity of these diols. Since these are dihydric alcohols, so obviously you will expect to get a monosodium and a disodium salt. So, all these reactions are nothing but we have done earlier also for alcohols, but just a recap or maybe for you to know that it works the same way with diols as well. So, you take the 1,2 diol, the only thing we are showing here is it takes place sequentially one by one. So, at 50 degrees, let us say lower temperature conditions, you replace the first hydrogen, and then for removing the next hydrogen from the diol, you have to elevate the temperature, and this is how you get the disodium salt. This is when you have both the hydroxyls as a 1 degree alcohol. If you start with a mixture of a 1 degree and a 2 degree, you will expect some preference of one over the other depending upon the relative acidity of the two hydrogens of the hydroxyl. So, this is a 1 degree and this is a 2 degree. So, when you do this reaction with the sodium metal, you will expect the primary alcohol OH to get replaced, this being more acidic, we discussed earlier, and this is followed then by the replacement of the other hydrogen of the secondary alcohol to give you the disodium salt. So, this is the reaction involving the active hydrogen atom of the diol, and it gives you the monosodium and the disodium salt. So, another reaction of the diols is with acids. Alcohols on treatment with acids give you esters, diols are no different. So, you will end up with a monoester and a diester. So, it depends upon the stoichiometry of the reaction, the conditions, temperature, everything, and this will decide whether you will end up with a single product which is a diester completely, or you end up with a mixture of a monoester or a diester. So, that depends upon the stoichiometry of the reagents, the reactants and the conditions employed. So, you treat it with acetic acid, and you treat it now with another molecule of the acid, and you get the diester. Another reaction is with acetic anhydride, and this is what leads to acetylation of the alcohols. So, you start with glycol, treat it with acetic anhydride in the presence of pyridine, and you get the diacetylated compound. All these are reactions also known with alcohols. There is nothing new which we are studying except for the fact that these are now involving a 1,2 diol system. With halogen acids, this also we have done previously. For monohydric alcohols, there is a slight difference. So, if you recollect with halogen acids, we talked about treating it with HCl, HI, HBr, and I was telling you how with HCl we call that is a Lucas test, how that is going to precipitate out and tell you whether it is a primary, secondary or a tertiary alcohol. So, here also if you start with a glycol and treat it with HCl 160 degrees centigrade, loss of water molecule, you get a mono-substituted monohalogenated product, and with another equivalent of HCl, relatively higher temperature 200 will give you a dihalo compound. So, this is with halogen acid, the halogen acid being HCl or HBr. This is the reaction which it gives. But if your halogen acid is a HI, then the rules are slightly different. In fact, the product is slightly different. So, you treat it with HI, okay. So, I can directly write 2 moles of HI, 2 of water lost. So, you end up getting this as the product, but this is quite unstable and is not isolated, immediately undergoes dehalogenation and it gives you the corresponding olefin. So, if you start with a diol and treat it with HI, instead of getting the corresponding diiodinated compound, you get the corresponding olefin, and this is also true if you also take Pi3 instead of HI. So, basically it is the diiodo species which is not stable, it leads to the formation of this product. Okay. Another reaction in halogen acid, if it reacts, so halogen acids, and if it reacts with nitric acid, then what happens? This we studied earlier also. So, you now have the diol and you are treating it with nitric acid, which is, so since there are 2 hydroxyls, I will show it with 2 molecules, 2 moles of the nitric acid, and I end up getting this dinitrate along with loss of water. So, these are straightforward reactions dealt with earlier also. With PCl5, PBr3, what will happen to the diol? What was happening to your monohydric alcohol? Same thing will happen here also. So, you treat it with PCl5, you will get the corresponding dichloro compound. Important reaction in this category would be the reaction of diols with aldehydes and ketones. These are important reactions, aldehydes and ketones. So, with aldehydes and ketones, the diols end up giving us acetals and ketals as products. These acetals and ketals are the cyclic compounds, and the carbonyl is protected in the form of acetals and ketals when we carry out the total synthesis or in multi-step synthesis. So, in this case, this is what is used to protect them. If you have to carry out protection selectively, then we convert an aldehyde into an acetal. So, you treat this with the diol, okay. So, sequentially 2 steps, loss of water, and you end up getting this compound, the acetal, and the same thing if you do starting from ketone, then you again lose water, 1 molecule of water to give you the corresponding ketal. Okay, so, these are important reactions because this is one of the ways in which an aldehyde and ketone can be protected. So, it is used in protection deprotection strategy. Another reaction of a diol is a dehydration, which is again an elimination reaction, and there can be very many different conditions in which it can be dehydrated to give you different kinds of products. So, either you directly heat it without adding anything, or you add any dehydrating agent like a zinc chloride, anhydrous zinc chloride, or you treat it with phosphoric acid, or you treat it with concentrated sulfuric acid. So, different types of dehydrating conditions can be used. If you heat it, if you add zinc chloride, if you take phosphoric acid, if you take sulfuric acid. So, if you simply heat a 1,2-diol at high temperature, you end up getting the corresponding epoxide. So, an epoxide is the product from a diol if you are heating it without any added reagent. If you do the same thing using zinc chloride and you heat it, it again undergoes loss of, so it gives you CH2 double bond CHOH, loss of water. Here also all these are dehydration reactions, but happening in different ways, and this gives you vinyl alcohol unstable product, and it immediately rearranges to give you acetaldehyde. So, you get acetaldehyde if you treat it with dehydration with zinc chloride. Okay. The other reagent is phosphoric acid. Okay. In phosphoric acid, we start with 2 moles of your corresponding glycol, dehydration, loss of water molecule, but look at the link. The linkage is between one of these ethylene linked together and the other hydroxyls are free. So, what you get as a product is a diethylene glycol when you carry out this dehydration with phosphoric acid as the reagent. And the last one in this series, if you start again with 2 moles of this and you treat it with concentrated sulfuric acid, it undergoes now loss of 2 molecules of water instead of 1 as was happening with phosphoric acid, and in this case the product which you get by the loss of 2 molecules of water is this cyclic ether, which is called dioxane. It is a popular solvent used in organic synthesis. So, this is what happens when we carry out dehydration under different conditions. So, we get an epoxide, we get an aldehyde, we are getting a dioxane. So, all these different strategies are what makes this very interesting, and in the next class we are going to take up few more important reactions of these glycols, where we will talk about one of the important reactions I can talk about is the pinacol-pinacolone rearrangement. This is what we are going to discuss in the next class. So, stay tuned and revise what all we have done so far. Thank you.